Hello, I'm Renzo Huber, and this symposium talk is entitled Ultra-High Resolution fMRI in the Presence of Motion. And the conclusion of this presentation will be that, different to many other examples that you have seen already about head motion and its problems, in the specific context of high-resolution fMRI, motion is not such a showstopper. Rather, I think that in the context of fMRI, high resolution is actually the solution to head motion. And I will explain why I think that. I have no financial interest to disclose with respect to this presentation. First, let's be clear what I mean with high-resolution fMRI. I mean this research field of sub-millimeter laminar and columnar fMRI. It's an emerging and growing field since about quarter a century, with applications focusing on layer fMRI in basic cognitive neuroscience studies that use healthy, compliant, well-trained study participants. And while this field has technical challenges, head motion is not really the one that's most often discussed. So among the 250 papers published so far, only 3 single papers really focus on motion. And vice versa. Not only does high-resolution fMRI literature not care about motion, also the motion correction field does not seem to care about high-resolution fMRI either. So high-resolution fMRI was not part of any of the past workshops until the symposium today. And this disconnect between the two different fields is kind of strange, isn't it? So in high-resolution fMRI, people care about these very, very tiny small things, these little stripes here that might be interpreted as layers or columns or vessels. And at the same time, some of the raw data of the time series look something like this on the left over here. And this is a particularly bad example of obvious motion. So how can this be? How can we capture features of 0.5 millimeter thickness with head motion in the range of 3 millimeter? And the answer is that it kind of depends on the kind of motion. So different to other imaging, in fMRI we are looking at dynamics. So even in this very bad example, the actual resolution within the readout is very, very small. The big motion that you see over here is a motion that is accumulated across many TRs and repetitions. So within the standard fMRI processing, there is this retrospective motion correction processing alignment step that's really used in almost every single data analysis pipeline out there for high resolution. And that takes good care of this cross-TR motion, as you can see here, taking really out most of the bulk of the problem right there. There's still a bit of residual fluctuation going on here, as you can see, which comes from within TR motion, especially in the segmented multi-shot 3D EPI methods like this one over here. This is kind of a form of spin history effects in EPI or coming from EPI phase errors like these flickerings across the TRs, which can, again, still be censored in the analysis later. So you're taking those data out of your time series and then are ending up with very clean time series, as you can see them right over there. So in fMRI, as long as people don't move constantly, like all the time, the motion-related dropout rates or data sets that are not usable due to motion, it's not really something that limits us from pursuing a certain study. Okay, let's look a bit into the details of how this retrospective motion correction is done. Namely, there are 2 stages. First, a computer algorithm needs to estimate the spatial misplacement, and then this information needs to be used for image correction. Let's start at the first stage, where here Wang et al. From Polymeni and Rowe's lab looked at the accuracy of ground truth high-resolution data across resolutions. And they found that the lower the resolution, the more residual errors you have. So having more high-resolution details in your fMRI images helps for the accuracy of your motion estimation. So for the motion estimation, it helps to go to higher resolution. And then we just need to correct for it, which is usually performed as a spatial resampling step that estimates kind of the spatial partial volume of a voxel and then puts the signal back into the location where it should be. And from an imaging processing point of view, this can result in kind of signal leakage and apparent blurring, which can be mitigated, for example, by working on a finer spatial grid, reducing the blurring effect of such images based on these voxel models. So again, here, resolution helps. However, to be really honest, I don't really share these concerns of signal blurring due to spatial resampling a lot, because this is not really how fMRI or MRI acquisition works, that we have these voxels of homogeneous signal distribution within the voxel and then these sharp borders. Our voxel in fMRI rather look like something like this, right? Due to the nature of the acquisition. So we don't really have sharp edges to begin with. So based on Oliver Speck's equations that we probably saw in the first presentation, there is a mathematical formulation that achieves a completely blurring free resampling. For example, you can perform a translation operation simply by adding a phase gradient in case space, right? And then for the image processing, it's rather a matter of getting the right interpolation function that best describes this kind of behavior. And with respect to that, I like Bob Cox's empirical test to rotate the brain 360 consecutive times in 1 degree steps, and then see if the brain, after applying this resampling operation 360 times, and you still see if your end image looks like the one that you started with. Where you can see here for different interpolation functions that it really matters. For example, doing a nearest neighbor interpolation, you get these kind of weird sharp edges where they shouldn't be. For a linear interpolation, you have this accumulation of signal leakage. But if you use a Hamming filtered sinc or a spline 5, you can already see that the interpolation step, even though you have many of them, doesn't really affect the data quality. Next, I would like to show some extreme examples where motion in high-resolution fMRI can be specifically annoying. In some of those cases, they can be maybe even a showstopper. So here you see motion across a 90-minute time window, which is representative, I think, the amount of motion here. So if we don't do any motion correction, like at all, and just average all the data that we get across these 90 minutes, we get this kind of mean image. Which doesn't look too bad, does it? Right? Given that you clearly see that the brain is moving a lot, we still kind of see a lot of contrast. So there's still a structure. Yes, it's blurry, but across the entire time series, a voxel that might be kind of up there still has a higher probability of capturing superficial layers more often than the deeper layers. And a voxel kind of down there has a higher probability of capturing signal that's close to the white matter, right? Because it's close to this border. And we still see this border. If I pump this through a conventional motion correction pipeline and average all the time series, it looks much crisper, so we don't have these blurring due to motion. However, still, you see that it's not really perfect for these high-resolution protocols, as you would expect. Because many of these slab protocols that we are using for layer-dependent fMRI, we have these kind of slabs and borders, and the outermost slices have a different spin history compared to the innermost slices, or a slightly different flip angle in 3D protocols. So the algorithm tries to really align the brain within the plane, but across the slab, it's not perfect. So you can tweak the analysis a bit to estimate the motion mostly on the inner slices with higher weighting factors as opposed to the outer slices. And then you see that even in these coronal views that the brain is stable now. It's just the border of the slab that kind of seems to be moving up and down. So it can help a lot when you move your motion pipelines from conventional resolutions to high resolution by really optimizing the motion estimation in some slices more than others. And this trick of locally restricted motion estimation can also be helpful in cases of nonlinear motion, because sometimes it looks like the brain seems to move differently compared to the rest of the image. Here, for example, you can clearly see that the skin is differently moving from the brain. So you want to optimize the motion estimation only in the area that you care about. This trick of locally specific motion estimation is not really sufficient anymore for alignments like this. Whereas at these low bandwidth EPI readouts that we always need, and we are specifically sensitive to nonlinear motion, specifically to local distortions. And since in layer-dependent fMRI we are dealing with very noisy data, very often we want to average signals across many sessions. And obviously there's a lot of motion happening across different sessions. So there we need nonlinear models like this Arndt's SYN algorithm that can account for most of it. These nonlinear motion estimations, however, also have their limits. They need to be applied at the right spatio-temporal scale and need to be constrained to that scale. So here we have an example of a very strong task, a tapping task with a clear on-off paradigm, where in the raw data you can even see here at the blue arrows that it's getting dark, bright, dark, bright. So you clearly see the activation with the naked eye. And then when you pump this through these nonlinear motion estimations, you can see that we have kind of shrinkage, less shrinkage, shrinkage, less shrinkage. So the motion algorithm tries to account for these signal changes across time by interpreting it as motion, reducing some of the variance that we are interested in. More advanced approaches of alignments are needed when it comes to single slice experiments here, where Paul and Divya show a solution at this conference on how to get the best approach for single slice experiments. They have a framework of streaming data in a socket-based approach automatically offline to the scanner and then override the vendor-provided scout matrices. And then they see with very high in-plane resolution individual vessels and their functional responses. These field of view prescription changes are particularly also helpful for line scanning. So here you see an example of Tyler Morgan that uses localizer scans, which are then pushed through orientation matrix gymnastics to end up with a line exactly where you wanted to have from a previous session. But you can use these kind of prescription changes not only on a session-by-session basis or run-by-run basis, but also on a TR-by-TR basis, which is then commonly referred to as prospective motion correction. Here is an example from Dr. Raimondo for layer-specific line scanning, which uses fat navigators that take good care of these motion spikes over here. Or you can also use camera-based approaches that we heard about already, limiting the residual motion of sub-millimeter fMRI, as shown by Jonas Pause. Maybe even harder examples of motion in high-resolution fMRI refer to task-correlated motion, like here, where in this example, people are doing a very hard alphabetization task, and you're looking at the respiration curve, where you can see that during most intense periods of the task, indicated in black, people are really focusing on the task. They almost forget how to breathe. And then sometimes, only sometimes, right after these intense periods, people take a deep breath of relief. So the activation maps at the end look basically like task-locked EPI artifacts. And there's very, very little you can do about that. You can still try to untangle the time series of these task-locked motion artifacts, which are manifested in MRI data like instantly, compared to the fMRI responses that are kind of delayed due to the HRF. But it's not going to look as clean as you want to have it if you have task-correlated motion. In fMRI studies, it's not only the motion in the fMRI data themselves that are annoying, but even more often I'm annoyed by motion in the structural reference data that we need to analyze our fMRI data. Simply because it takes longer to acquire those data, it happens more often that we have motion compromised structural scans, for example, these typical rings, as you can see here. And a mitigation strategy with great potential is shown on Wednesday by Kenny, who uses an MP2Rage-like sequence, but with a 3D EPI readout, and then having a few averages where you can see that when there's motion, it's usually affecting one of those averages, and then you can censor this average and still use the remaining data to get nice and clean structural reference data out of it. And since the 3D EPI MP2Rage approach is so fast that you get an entire volume in just 20 seconds, you can even run functional experiments right during your structural reference scan that allowed me to get a new appreciation for a completely different form of motion yet. Namely, you can put the second inversion time, push it through GLMs like you would do for conventional bold imaging, and at the same time you can use the T2 star free uni image and use it for structural analyses as a dependence of function, where you can see that there are tiny changes in T1, and FreeSurfer interprets these tiny changes in T1 as a gray matter dilation. Specifically, the border between gray matter and white matter seems to move inward. So in the visual cortex down there, you can see how the borderline between gray matter and white matter seems to move inward as interpreted from FreeSurfer. And this is specific to the visual cortex. Here, for example, in frontal areas as a control, you can see how stable these lines are. And here we are not seeing these functional changes. And there's very little literature about task-based structural changes. And nobody really knows how much there are implications for the interpretation of fMRI. So most researchers just ignore it. After these examples where motion can be annoying, let's also talk about examples where motion is less annoying than expected. Namely, for example, with respect to brain motion, which version D might talk about more later. So my boss's boss, the NIH director, has sent deceptive tweets like this, showing a motion amplification model that synthetically amplifies cardiac-induced motion from a low-resolution distortion field. So to see how relevant this is for high-resolution fMRI, I also wanted to look at it with a high-resolution EPI protocol that we would use for layer-dependent fMRI. So here you can see that the raw time series, they show that there's a lot of stuff going on, right? That there's fluctuation down there in the CSF, there's kind of noise a bit. So to better appreciate the cardiac-induced motion, you can see here in the underlay the mean of the motion and the mean of the signal, where you see that there are these very fine stripes visible. They're not blurry at all. So if there's motion, there doesn't seem to be a lot of motion. Most of the signal changes are coming from motion kind of in the vessels or like right around the brainstem in the CSF. And you can even better appreciate this with a longer echo time where you see the CSF kind of flushing through and then even going to the sulcal spaces over there. But in any case, I don't see indications that the brainstem is moving a lot. And again, in this case, I think resolution helps to mitigate motion because it keeps the moving parts, namely the CSF, in the locations where it should be, namely outside the tissue. And you cannot use a low-resolution motion method to describe this. Another thing that I found not as bad as expected are motion effects in 3D EPI and multi-shot methods compared to 2D. Quite the contrary, actually. So in accelerated 2D EPI, we have these weird interleaved slice acquisitions, so neighboring slices are not acquired consecutively in time. So in this example, you can see that when there's head tilting, like for example for a respiration task that we're looking at here, you see that the brain is moving with respect to these kind of borders. So after retrospective motion correction, the brain is now still, but these borders are moving. So the individual slices have these artifacts like this anterior-posterior kind of brightening and darkening. So when you're looking at respiration-induced signal changes, you see that there are the vessels visible, yes, but they are kind of hidden under this huge artifact. Now in 3D EPI, we are not acquiring slices consecutively, but the entire volume over and over again and just vary the different spatial frequency weights to end up with the same resolution. And then when we have motion in 3D EPI, we don't have these different spin history effects. So after removing the respective head tilting here and look at a given slice, we don't have this anterior-posterior bias and we can see the vessels much, much clearer. Finally, as we will learn from David in the later lectures too, prevention is better than cure. Where in high-resolution fMRI, we are a bit privileged. Namely, in most fMRI studies, we have the luxury to simply blacklist participants that cannot lie perfectly still, and we scan them never again. Motion prevented. I also found it very helpful to let participants watch their favorite show. I learned this from my kids too. Give them something to watch and they sit still like a statue. And while there is scientific evidence that Netflix improved data quality, I could not yet convince my institution to buy a subscription for me. And obviously this is only applicable for some functional studies. Many of my layer fMRI colleagues like these inflatable cushions. I also found it a very efficient strategy to make a person very motivated to lie perfectly still by giving them feedback. Just tell them that they moved. Tell them that you need to repeat the scan again and now they're not gonna get out early. Some layer fMRI researchers also like the solution of using medical tape to give haptic real-time feedback of head positions, which is well tolerated. Another, maybe more cumbersome solution is to use these individualized head cases. Even more extreme would be to use a bite bar, which I have been told is not the favorite solution of some of the participants. There is some exciting abstracts of motion correction for fMRI at this conference, and one of them is even on high-resolution fMRI, so check them out. In conclusion, for high-resolution fMRI, I don't really see clear evidence that head motion is holding us back. At least not for EPI-based acquisitions that can be corrected for retrospectively. In fact, one of the early selling points for EPI was its ability of dynamic scanning to quote-unquote freeze motion. We know that layer fMRI has limits, but motion is not among the major of those limits. And now I would like to thank all the contributors of slides, and I thank you for your attention.